Imagine a world completely cut off from the sun, not just dark, but miles deep, under a sheet of ice so thick it would make Everest look like a molehill.
Yeah.
And then imagine finding an entire vast body of water down there, hidden for millions of years, and then discovering life thriving within it.
It really does sound like something out of a science fiction novel, doesn't it? Yet it's not fiction at all.
Right.
Today, we're taking a deep dive into the incredible reality of subglacial lakes, these massive reservoirs of liquid water trapped beneath Earth's colossal ice sheets, some untouched for eons.
And our mission for this deep dive, as we explore these sources together, is to uncover exactly how scientists have managed to discover, explore, and even, sample these impossibly remote environments.
And beyond that.
What's even more mind-blowing is what the discovery of life within them means for understanding life's astonishing resilience right here on Earth, and what it might mean for the potential for life far beyond our planet.
Exactly. For this journey, we've pulled from a fascinating stack of sources. Everything from pioneering scientific papers that first hinted at these hidden worlds to detailed modern research findings and thrilling expedition reports. It really paints a picture of the evolution from early speculation to the cutting-edge research happening today.
Okay, let's unpack this.
Yeah.
Because the sheer difficulty of identifying and studying something so profoundly hidden beneath miles of ice is almost impossible to wrap your head around.
It really is.
It's like trying to find a needle in a haystack. If the haystack was frozen solid and bigger than a continent, and you couldn't even see it. The ingenuity involved in seeing something totally invisible. It's truly remarkable.
That's a great way to put it. For decades, the very existence of these lakes was largely theoretical. Then, in the late 1950s and early 1960s, a Russian geographer named Andrei P. Kapitsa pioneered a technique that provided the first concrete evidence, seismic sounding.
Seismic sounding? That sounds incredibly complex.
Yeah.
How did Kapitsa's team even begin to figure out what was under all that ice using that method?
Well, their approach was groundbreaking for its time. Kapitsa's team would drill these 50-meter deep holes into the ice.
50 meters, okay.
Yeah, then set off small explosions. The sound waves would travel down through the ice, reflect off whatever was beneath, and then travel back up to be recorded.
So like an echo, but through ice.
Precisely. By measuring the time it took for the wave to return and knowing the speed of sound in ice, they could effectively map what lay below. This pioneering work led directly to the discovery of Lake Vostok, which remains the largest known subglacial lake.
That's an incredible just wow.
Yeah.
But how did they go from detecting one lake to systematically mapping entire hidden systems across a whole continent? That seems like a huge leap.
It was. And that's where radio echo sounding, or RES, comes into play. Also happening in the late 1950s and 60s, you had English physicists Stan Evans and Gordon Robin pioneering RES for mapping ice thickness.
Right, for the ice itself initially.
Exactly. Then, between 1971 and 1979, RES instruments mounted on aircraft extensively profiled the Antarctic ice sheet. This gave us an unprecedented wide area view beneath the ice.
Okay, so planes flying over with radar, essentially. But when they're looking at all this data, how could they reliably tell, okay, that's a lake, and not just, bedrock or some other weird formation under the ice? What were the telltale signs?
That's a great question, and what's truly fascinating here is that subglacial lakes leave very specific signatures. They're almost unmistakable once you know what to look for.
Like what?
Okay, first, you'd see an exceptionally strong reflection from the ice sheet base, significantly stronger than a typical ice-bedrock interface.
Stronger, so the signal bounces back harder.
Exactly. Second, these echoes maintain consistent strength along the survey track, which indicates an incredibly smooth surface below the ice. Like water.
Right, smoother than jagged rock. That makes sense.
And third, the reflection is notably flat and horizontal with slopes of less than 1%, so very level.
Got it. Strong, smooth, flat.
Those three characteristics together are the crucial identification markers for a subglacial lake. And this widespread RES mapping also revealed something else huge. Many of these lakes are interconnected.
So not just isolated ponds.
No, it hinted at a vast subglacial hydrological system, a whole network under the ice.
So we went from literal seismic bangs to planes flying over, mapping these hidden worlds from above. It's amazing how far the technology has come, and I hear there are even more advanced methods now. Still looking from a distance.
Absolutely. Modern research builds on these foundations. They now use sophisticated airborne RES data, like from the British Antarctic Survey's BBAS survey, and a method called bed reflection power, or BRP.
BRP. Okay, how does that work?
It involves identifying those really bright reflections we talked about, but then correcting for ice attenuation, basically, accounting for how the ice itself weakens the signal.
Like sound getting muffled through a wall.
Exactly like that. Then they classify the confidence level of the identification based on several stringent criteria. They also factor in things like hydraulic potential and the slope of the ice surface itself.
And what was the practical impact of refining this method? Did it find more lakes?
It was astonishing, actually. This refined method led to the discovery of 33 previously uncharted subglacial lakes just in West Antarctica.
The 33.
Yep. That's a 40% increase in the known lakes in that specific region, all from improving how we see through the ice from the air.
Speaking of seeing from above, satellites must play a role too, right? They measure ice all the time.
They absolutely do, and it's another really ingenious approach. Missions like NASA's IceSat and Cryosat-2 use satellite altimetry data. They detect and monitor subglacial lakes by observing tiny, subtle changes in the ice surface elevation.
So the ice surface actually moves up and down.
Slightly, yes. If the ice surface rises or falls, even by a small amount, it can indicate that a lake underneath is actively filling or draining. Earlier RadarSat data in the early 1990s also helped map these active lakes. This satellite-based approach was key. It allowed scientists to map the first continental-scale distribution of active subglacial lakes across Antarctica, showing us these dynamic systems were much more widespread than anyone thought.
Okay, so from sound waves, radar, satellites, we get an idea of where these hidden bodies of water are, but then you have to figure out what's happening within that system, how water flows, how it connects, right? How do they model that?
That's where computer modeling and digital elevation models, or DEMS, really come into their own. Scientists develop new DEMS of the basal topography, the shape of the land under the ice, using existing data, ice thickness measurements, and new radar info.
Right.
They then use these DEMS to create hydropotential models. Think of them like sophisticated plumbing diagrams for the subsurface. These models simulate the entire subglacial hydrological network. They characterize the basal hydrology and assess connectivity by showing us precisely how water flows, essentially, from areas of high pressure to low pressure, almost like a massive hidden river system under the ice sheet.
And this isn't just for Earth, is it? I remember reading these models have implications beyond our planet.
You're absolutely right. These very same kinds of computer models also help predict the potential behavior of liquid water reservoirs trapped in ice on other worlds. Think Jupiter's moon, Europa.
Europa, yeah.
It's a remarkable example of how research into Earth's extremes can directly inform our search for life elsewhere.
So we've covered the amazing ways we detect these lakes, map them, model their hidden dynamics. But the ultimate goal, the real dream, must be to actually touch these lakes to get direct samples. That sounds like an engineering and logistical nightmare.
It is an immense challenge, a monumental undertaking, really. It pushed the boundaries of engineering.
I bet.
Direct sampling expeditions require incredible precision, logistical prowess, and not to mention really stringent environmental protection. You cannot contaminate these pristine environments.
Absolutely crucial.
So after over a decade of meticulous planning, 3 major attempts were made, quite close together actually, in 2012 and 2013, to access, measure, and directly sample these Antarctic subglacial lakes.
Okay, tell me about them. What happened with Lake Vostok first? That's the biggest one.
Right. Russian scientists were the first to actually drill into the top of Lake Vostok in February 2012. They successfully recovered a frozen sample of surface lake water, which is known as accretion ice. It had basically frozen onto the bottom of their drill bit within the borehole.
Frozen lake water, okay. And then there was Lake Whillans, which I recall was a big success story for the U.S. team.
Precisely. The U.S.-led WISSARD project that stands for Whillans Ice Stream Subglacial Access Research Drilling. They successfully drilled cleanly into subglacial Lake Whillans in January 2013. This was a shallower lake known to be hydraulically active.
How did they do it cleanly?
The WISSARD team used a specially designed hot water drill system with filters and UV sterilization to melt through the ice without introducing contaminants. They even deployed a small robotic submarine.
A submarine under the ice sheet.
Yeah. Called the Microsubmersible Lake Exploration Device. It had sensors and cameras, and crucially, this project obtained water and sediment samples that definitively proved the existence of microbial life and active biogeochemical cycling within the lake. That was huge.
That sounds like the breakthrough moment for finding life down there. But given the sheer difficulty, I imagine not every attempt went perfectly smoothly. What about the other expeditions?
You're right to point that out. It's incredibly difficult work. In December 2012, a UK team attempted to sample Lake Ellsworth, which is much deeper than Whillans. But unfortunately, they were unsuccessful due to equipment and operational failures with their drilling system.
Ah, that's tough.
It was. But they gained invaluable operational knowledge from that attempt, which really fed into future projects. And then more recently, the SALSA team, Subglacial Antarctic Lakes Scientific Access, they reached Lake Mercer in December 2018 and January 2019.
Okay.
They also used a high-pressure hot water drill, similar tech, and successfully collected both water and sediment samples from Lake Mercer.
So multiple successful sampling missions eventually.
Yes, and these efforts really highlight the critical role of international cooperation in thoroughly exploring these unique, challenging environments. No single group can do it all.
So after all that incredible effort and ingenuity, finding these hidden worlds, figuring out how to reach them cleanly, what did they actually find? This is where it gets really interesting, right?
Oh, absolutely.
For decades, the assumption was these deep, dark, isolated environments would be sterile, lifeless. But that's completely overturned now, isn't it?
Completely. The fundamental insight here is just how wrong that assumption was. The discoveries have radically expanded our understanding of habitability even here on Earth.
It's hard to even picture the conditions.
Imagine extreme cold as low as -3 degrees Celsius. It stays liquid because of the immense pressure, which lowers the freezing point.
Right.
Then you have crushing hydrostatic pressure exceeding 400 bar in Lake Vostok.
400 times atmospheric pressure.
Exactly. Permanent darkness, obviously. And they're ultra-oligotrophic, meaning very, very low in nutrients. Almost starved. Oxygen availability can also vary and be quite limited.
And yet,
life thrives. It truly makes you pause, doesn't it? To think that even in such seemingly impossible conditions, life finds a way to not just exist, but truly thrive.
it still seems almost impossible, even with, well, we'll get to chemosynthesis, but surviving that cold and pressure. What makes these microbes so incredibly resilient? Is there a common thread?
Well, the diversity in how they adapt is truly remarkable. Take Lake Whillans, the WISSARD project found a staggering 130,000 microbial cells per milliliter of water.
130,000 per mil.
That's a lot. It is. And nearly 4,000 different bacterial species identified through genetic sequencing. And these weren't just dormant cells waiting for better time.
They were active.
Yes, actively metabolizing ammonia, methane, and sulfur compounds found in the 120,000-year-old sediments at the lake bottom. This proved active biogeochemical cycling beneath the ice sheet, essentially demonstrating a fully functioning ecosystem running in the dark.
Wow. A whole ecosystem based on chemicals, not light. What about Lake Vostok, the big one? Did they find similar things in that accretion ice?
From Lake Vostok's accretion ice, yes, scientists found evidence of actively growing bacteria and thousands of unique DNA sequences from bacteria, archaea, and even eukaryotes organisms with complex cells like ours.
Eukaryotes, too. Like what?
There were even intriguing suggestions based on DNA fragments of multicellular eukaryotes, things possibly related to freshwater daphnia, tardigrades, water bears, and even mollusks.
Seriously. Actual tiny animals.
Well, the DNA evidence suggested it, although it's really important to note that the potential for contamination by the drilling fluid, especially with Vostok's long drilling history, was a serious concern. So those eukaryotic findings are interpreted cautiously by many researchers.
Right. Contamination is always the big worry in these extreme sample studies. Okay, and Lake Mercer, the most recent direct sample, what came out of that?
Lake Mercer also provided incredible insights. Researchers discovered things like non-living diatom shells, remnants of photosynthetic organisms.
Diatoms. But how in the dark?
Likely transported there from sunlit surface environments long ago, perhaps when the ice sheet configuration was different, or carried by rivers before the ice covered the area. They also found crustacean carcasses, and get this, a tardigrade carcass.
Yeah, actual water bear body.
An actual tardigrade body, yes.
Mm-hmm.
Alongside bacterial concentrations of around 10,000 cells per milliliter. So again, evidence of active microbial life, and the carcasses suggest the potential for metazoan life, multicelled animals supported by that bacterial base, perhaps historically or even currently, much like we see in deep-sea vent ecosystems.
Okay, so if there's no light, How are these organisms getting energy? It can't be photosynthesis, obviously. You mentioned chemosynthesis.
Exactly. This is the crucial point, and it highlights one of the most incredible aspects of life in these environments: chemosynthesis.
Chemical synthesis, okay.
Organisms here derive energy not from light, but from chemical reactions with inorganic elements found in the water and sediments, things like iron, sulfur, nitrogen compounds.
So they eat rocks, sort of.
In a way, yes. For example, sulfide oxidation is a common strategy. Microbes gain energy by reacting sulfur compounds. This process, in turn, enhances the weathering of other minerals in the bedrock and creates these really unique biogeochemical cycles completely independent of sunlight.
Fascinating.
We've also found evidence of methanogenic microbes, those that produce methane, and methanotrophic microbes, those that consume methane. This highlights unique carbon cycling happening beneath the ice.
So there's a whole carbon cycle down there, too.
A significant one. And if these subglacial sediments, which hold large amounts of organic carbon and methane, were ever released, say, by melting ice sheets,
Oh, wow.
they could actually impact the global carbon cycle. It's a vast hidden process with potentially global implications.
That's a huge thought. And you mentioned these environments have been isolated for potentially millions of years. Does that mean they could be home to really ancient, unique forms of life? Like living fossils?
They absolutely could be. Some of these subglacial lake waters, especially in places like Vostok, thought to be isolated for maybe 15 million years or more, could harbor evolutionarily distinct microbial communities, lineages that have been separated from the surface world for geological timescale.
Like time capsules.
Exactly. These fossil waters offer invaluable insights into how life might have survived extreme periods in Earth's past, like the snowball Earth events, when our planet was largely covered in ice. They are living laboratories for understanding life's ultimate endurance and adaptation.
Okay, let's connect this to the bigger picture because this just blows my mind. If life can exist, can thrive in these seemingly impossible conditions on Earth, what does that mean for the search for life beyond Earth?
This is where Earth's subglacial lakes become truly vital for astrobiology. They are considered excellent analogs for potential extraterrestrial environments.
Analogs, like test cases.
Precisely. We're talking about the icy moons in our own solar system: Jupiter's moon, Europa, Saturn's moon, Enceladus, maybe even Mars in certain places. They're like our closest, most accessible training grounds for figuring out how life might work on alien ocean worlds.
So like a blueprint for exploring other worlds. You mentioned Europa and Enceladus.
Right.
What makes them so similar?
Well, Europa, for instance, is suspected to have tectonic activity, maybe, and we strongly believe it has a global ocean of pure or low salinity water beneath its thick ice shell. Sounds familiar, right?
Very familiar. Antarctica underground.
And Enceladus. We know it has an ocean of liquid water beneath its frozen surface because we've seen plumes erupting from cracks near its south pole.
Plumes, right? Spraying water into space.
Exactly. An analysis of those plumes found evidence of molecular hydrogen, which suggests ongoing hydrothermal reactions on its seafloor, a potential energy source for life, just like deep-sea vents on Earth.
Wow. And didn't you say they found gene sequences related to hydrothermal vents in Lake Vostok?
That's right. Finding those gene sequences associated with hydrothermal vent bacteria in Lake Vostok ice further strengthens this analogy between Earth's hidden lakes and these potential ocean worlds.
And Mars, too. I think I read something about a lake there.
Yes, you're right about Mars. A really significant discovery back in 2018 made using radar echo sounding from the Mars Express orbiter.
Same technique is used in Antarctica.
Essentially, yes. Adapted for Mars. It found evidence of a stable body of liquid water, a subglacial lake, beneath the southern polar ice cap of Mars. It proved that these hidden water worlds aren't unique to Earth.
So, studying these deep, dark, cold places on Earth isn't just about understanding our own planet. It's actually helping us figure out how to find life out there.
Precisely. Studying Earth's subglacial environments helps astrobiologists develop and test the very technologies we'll need for future missions to these ocean worlds.
Like the drills in the little sub.
Exactly like the hot water drills and robotic submarines like WISSARD's microsubmersible lake exploration device. These are stepping stones, proving grounds for technologies that might one day drill through Europa's ice or swim in Enceladus's ocean. Even the remote monitoring with satellites and computer modeling we discussed that helps us practice gathering data remotely, preparing us for exploring places we can't easily reach.
So what does this all mean for our definition of habitability? Where life could exist, it sounds like it completely changes the game.
It absolutely does. These discoveries fundamentally expand the concept of planetary habitability. The compelling evidence that life exists and is active in these seemingly inhospitable environments on Earth provides a powerful argument that life could exist in similar conditions beyond our planet.
It makes those icy moons seem much more promising.
Definitely. It shifts the astrobiological focus increasingly towards these ocean worlds as prime candidates for extraterrestrial life. It shows us that maybe all you need is liquid water, an energy source, even chemical energy, and enough time, even if it's hidden beneath miles of ice. It suggests subsurface liquid water bodies might be common habitats across the universe.
It's just an incredible journey. From those first kind of crude seismic soundings decades ago to drilling miles down into hidden lakes and finding these thriving microbial cities, these discoveries really change our perspective on the very limits of life, don't they?
Indeed, it demonstrates the astonishing resilience and adaptability of life, capable of colonizing environments that not so long ago we thought were entirely sterile, totally impossible.
And it leaves you with such a provocative thought, doesn't it? If life can find a way to thrive in isolated, dark, high-pressure environments beneath miles of ice here on Earth, what other incredible forms of life and what other hidden worlds might still be waiting to be discovered, both on our own planet
There could still be surprises here.
and across the vastness of the cosmos? What might you, listening now, want to explore in your own deep dive next?